In this video, we are going to study two objects moving along respective circular paths. At t equals to 0, the objects are side by side and a reference line has been placed that passes through the two objects and through the center of the circles. As time proceeds, the objects move along their respective circular paths. An interesting question to ask is, what is the shortest time after which they are going to be side by side again? To answer this question, we need to understand the difference between angular displacement and angular distance covered. The angular displacement of an object from a reference line is the angle theta between the reference line and the radial line. However, the angular displacement theta must be between 0 and 2 pi. This means after each revolution, when the object passes the reference line, the angular displacement theta is reset to 0. On the other hand, the angular distance covered, alpha, is the total angle swept by the radial line. Here at that instant, after completing one full revolution, the angular displacement of the object is theta. The angular distance covered, alpha, by the object is alpha equals to theta plus 2 pi times 1. If it has completed two full revolutions and it is at an angular displacement theta, then the angular distance covered alpha is alpha equals to theta plus 2 pi times 2. If it has completed three full revolutions and it is at an angular displacement theta, then the angular distance covered alpha is alpha equals to theta plus 2 pi times 3, and so on. Now, we can generalize this result. After n full revolutions, when the object is at a displacement theta from the reference line, the angular distance covered alpha is theta plus 2 pi times n. The values of n takes values 0, 1, 2, 3, 4, and so on, depending on the number of full revolutions completed. When n equals to 0, we have alpha equals to theta, meaning the angular distance covered is equal to the angular displacement from the reference line. This happens because the object has not yet done one full revolution. The angular distance covered, alpha, is related to time t via the equation alpha equals to omega t, where omega is the angular speed. This means we can rewrite the equation alpha equals to theta plus 2 pi n in terms of omega as follows. Omega t equals to theta plus 2 pi n. Now let us apply this equation to our two objects A and B. For the objects A and B, we can write respectively omega AT equals to theta A plus 2 pi NA and omega BT equals to theta B plus 2 pi NB, where theta A and theta B are their respective angular displacements from the reference line. Now let us see what happens when the two objects become side by side. When the two objects become side by side again, we have theta A equals to theta B. Using the two equations, we can equate theta A and theta B and have omega AT minus omega BT equals to 2 pi NA minus 2 pi NB, which can be rearranged to obtain T as T equals to 2 pi NA minus 2 pi NB over omega A minus omega B. And there it is. We have obtained the values of t at which the objects are side by side. Now, if we remove 2 pi in this equation, then we have t equals to 2 pi in bracket Na minus Nb over omega A minus omega B. The quantity Na minus Nb is simply the difference in the number of full revolutions between the faster object and the slower object. And this will always be a whole number. Remember, in our example, the object A is our faster moving object, meaning it has a greater angular speed. So let m equals to Na minus Nb, and we can write t equals to 2 pi m over omega A minus omega B, where m takes values 0, 1, 2, 3, 4. When m equals to 0, this corresponds to the initial time t equals to 0 when they are side by side. When m equals to 1, this one corresponds to the shortest time after which they are side by side again. And for other values of m, then we have other times when they are going to be side by side again. Hence, the shortest time after which the objects are going to be side by side again is simply t equals to 2 pi over omega A minus omega B.